All right, this is a challenging homework assignment. So we're going to do it because this is going to get you ready for a test. All right. You are standing 2.5 meters and directly in front of one of the loudspeakers. So here's you. Right here's the speaker. There's you. The speakers are 3 meters apart. They're both playing 686 hertz in phase. Okay, as you begin to walk directly from the speaker, at what distances from the speaker do you hear a minimum sound? Now, what's going on here? Well, think about it. Look at, these guys are in, right? It says they're in phase. But there's a path difference. So here's a path from this speaker. Here's a path from this speaker. If the path difference is one wavelength, constructive interference. If the path difference is a half or 3 halves or whatnot, we're going to have destructive interference. So you're going to hear a minimum. So basically, look at, as you're walking here, you know, when there's a path difference of a wavelength or 2 or 3 or 4, you're going to hear a maximum sound. If the path difference is half or 3 halves, whatnot, you're going to hear a minimum. So what's it really going to sound like? If you're walking like this, you're going to hear something, then you're not going to hear something. Then you're going to hear something, then you're not going to hear something. That's actually going to happen. If we were in meeting face-to-face, I would actually set something like this up out in the grass area outside of McKay 132. What I did instead, though, I had a speaker and a speaker, and we would walk this way. But it's the same thing, right? Sometimes the path difference would be a wavelength. Sometimes it would be a half a wavelength. So as you walk, you'd hear loud, nothing, loud, nothing, loud, nothing. I mean, it's cool, you know? All right, but anyway. All right, so we want to see, at what distances from the speaker do you hear a minimum? Now notice it says distances plural. So there's going to be more than one location. Oh my gosh. Right, let's do it. Okay, so, okay, so here's a speaker, and here's a speaker, all right? And this is what we want to find out, this distance. So we're going to call it D1 for no good reason. D1. And we know this is 3 meters, right? And this is you. And you're walking this direction. All right? So this is the path difference from the top speaker. I'm sorry, this is the path length for the top speaker. This is the path length, I'll call it D2, from the bottom speaker. Right? So path length 1, path length 2. Okay. Now, it says we want to hear a minimum sound intensity, so quiet, right? So that means that the waves have to interfere destructively. So that means that the path difference has to be a half or 3 halves or whatnot of wavelengths, right? So we're going to, we can write this as m plus 1/2 lambda, where m equals 0, 1, 2, on and on. Okay? By the way, if we wanted to, we could have said m minus 1/2 lambda, where m equals 1, 2. I mean, who cares, right? It doesn't matter. Do that or do that, whatever you like. It doesn't matter. Okay, so there you go. All right. Now, first of all, we don't even know what the wavelength is, right? All we know is the frequency. Okay, so what are you going to do? What do you always do for waves? F equals ma, right? Okay, so lambda equals v over f. Okay, so why did they tell us that the temperature is 20 C? Because the speed of sound depends on temperature. So you have to look up in the book. At 20 C, the speed of sound is 343. So speed is 343 meters per second. That's kind of like that's just like the standard average speed of sound, right? 343. The frequency, oh, aren't these guys nice? Look at that. Isn't that incredible? 343, 686. Woohoo! Half. Okay, so the wavelength is a half a meter. Now, this question is a pain, all right? So the path difference, what's the path difference? It's D2 minus D1. D2 minus D1. Okay, so what we want destructive, right? We want destructive interference. So therefore, we want the path difference, d2 minus d1, to equal what I just said, m plus a half wavelength, right? And we're guaranteed to get that minimum. Now, what we got to do, oh golly, we got to solve, right? We got to solve for this thing. Oh golly, how are we going to do that? Well, Okay, so let's see. I have two variables here. I don't like that, right? We just want one variable. So let's see. What's d2? Well, just Pythagorean theorem. Come on, right? So look at. So forget about units. No units. Sorry. So 3 squared is 9 plus d1 squared equals d2 squared. All right, fine. Okay. So let's do that, right? So d2. So d2 is this. Okay. All right. So d2 is 9 plus d1 squared, square root of. So 9 plus d1 squared minus d1 equals m plus 1/2 lambda. Ugh. Now look at that. That's sort of awful, right? So let's make it a little bit nicer by putting d1 over here. So add a d1. It's still a mess, but hey, we're going to need to do what do you do? So now you got to square both sides. Yuck! Square both sides. 9 plus d1 squared. Square both sides. You got to be kidding me. No, I'm not kidding you. Square both sides. M plus 1/2 squared lambda squared plus 2m plus 1/2 lambda d1 plus d1 squared. Oh, that looks ugly. All right, now, wait a second. Well, hey, that's not so bad. At least we can get rid of that. Get rid of that. But come on, it's still a mess, you know. Okay, so solve for d1. So d1, it's over here, right? Okay, so d1 equals 9 minus that. Divided by 2m plus 1/2 lambda. Yep. All right. Now, does that simplify? No. What are you going to do, right? What are you going to do? So you just deal with it. All right. Now, so what? It's okay. We can handle it. So we just have to find out the distances, you know? So just make a table. Just make an m and a d1. So, you know, 0, 1, 2. You just, I don't know, I get sick and tired after that. All right, so just plug it in, you know? Just plug everything in. Just plug it all as junk in with m equals 0, 1, 2, 3. I promise you, when you do that, you get 17.9. This is meters. 17.9, 5.6. 3.0, 1.7. Now, hold it. Gotta be careful. It says you're stating 2.5. This is 2.5 meters, right? That's 2.5 meters. So forget about this one, right? All we want are these three. So these three would be the answers. There you go. So make sure you understand that one. You might see something like that again. All right. I'm not going to do this. You do it. This would be practice for you. But let me give you the answer, though. I have it somewhere. Okay. So for this problem, the answers are, let's see. Now notice it says, what two wavelengths of light are most strongly reflected? Okay? 2 and, all right, 2. Okay, so the answers are 720 nanometers and 432 nanometers. Right? So you do that, please. So it's C, right? C. All right. let's, this is what we did. We hopefully understand and apply the principle of superposition. Standing waves are the superposition of two traveling waves, right? One wave goes this way, reflects, comes back. At certain frequencies only, you get standing waves, which are not traveling waves. Okay, we studied the properties of standing waves in gory detail. We figured out where the nodes and the antinodes and everything, and we figured out the frequencies. We talked about interference in 1 and 2 dimensions, 2 and 3 dimensions. How come it doesn't say we did sound waves, right? Columns of air. We learned about standing waves in columns of air. I guess that's this one, right? We did transverse waves and longitudinal waves. And then beats, superposition of two waves of unequal frequency. Okay, so waves travel through each other. Two-dimensional interference, you see these interference patterns. Right, with two different sources, you get an interference pattern. Principle of superposition, just add displacements. Standing waves, the nodes separate every half wavelength. Antinodes, that's what antinodes are. Yeah, I already said that, right? So the string length is half a wavelength. Here the string length is 2 half wavelengths. Here the string length is 3 half wavelengths. So you can figure out all those relationships. Okay, then we did the closed air column. And again, this is a node because the air can't move. This is a node so the air can't move. It's a wave, so you just fit the biggest wave. Just this, right? And then the second one, 2 humps. Third one, 3. And we learned that the pressure and the displacement, opposite nodes and antinodes. Okay, this is just like a standing wave. And then we did an open-closed. Again, here, the displacement is a node because the air can't move here. So it's all node, node, node. Here the air can move. So open, so it's open, it's open, it's open, So you just fit how many waves you can get in there. Here's the biggest one, then the next one, and the next one. So you just draw these things, And then from these pictures, you can figure out the frequencies. And you should be able to do that without looking in the book. And then the open, displacement, antinode, you draw the pictures, you use V equals F lambda, you figure out the frequencies. Again, you have to do that by yourself. Yeah, we did all that. Standing waves on a string. This is the phase. This is the phase constant. How do you get a phase difference? Path difference or phase constant difference. You can see that in the equation we figured out. And then the thin films, if the reflection is from small n to large n, there's a flip, right? There's an inversion of the wave, and that's equivalent to a lambda over 2 flip, or shift. I guess shift, whatever. And then here, it goes from large to small. There's no flipping or shifting or anything like that. We use the analogy with a rope, right? With a phase difference of pi, it's equivalent to a shift of lambda over 2. Yeah. Oh my goodness, look at all these equations. Here's a standing wave equation, which we actually worked out. Here's the frequency for a standing wave on a string. These are the frequencies where you get a standing wave. For any waves, constructive, the phase difference is 2m pi. Destructive, this thing here. And then we did all this other stuff, right? This was just a general interference of waves. And don't forget this, right, when you do your thin film problem, because the thickness, the path difference usually, not always, usually occurs in the medium, so you have to use this. And then the beat frequency. That's it. Thank you very much.